we can reproduce this phenomenon, this transition from order into chaos, with a simple mathematical model of the cardiac cell. So we were talking about number one, we were talking about the pumps, and then we were talking about sodium ion and potassium ion, and sodium being low inside the cell and potassium being high, and then that's exchanged. The sodium flows in and the potassium flows out. And all of that creates a change in the voltage. So the model of this is a differential equation, which is basically V prime and sodium prime and potassium prime. And these are differential equations that say that the change in voltage is some function of sodium, potassium, and voltage itself, and that the change in sodium is some other function of voltage, and the change in potassium is some other function of voltage. These are straightforward differential equations. And look up cardiac cell modeling. There's a lot of examples. This is a very seriously studied subject. And you can make a fairly low-dimensional model that faithfully recreates the properties of the cardiac cell. Now let's take one of these models and let's drive it with a periodic stimulus. And so we're going to drive it with a nice, slow, periodic stimulus. And you see what the result is. We get a nice sequence of cardiac electrical activations, which are perfectly periodic. But when you start to give high frequency beating, now the beat is encroaching on the second beat is encroaching on the first beat, and we're going to get irregular beating, as you see here. So, bottom line, rapid pacing, rapid driving of the cardiac cell faster than the recovery time, which is what it takes the pumps to restore everything. Pacing the cardiac cell, or the cardiac cell pacing itself, faster than that recovery time is going to lead you into exactly the same situation as the dripping faucet, and is going to produce an irregular, chaotic train of electrical actions. And then when you plot that in Poincare, you are going to see the plot that we saw, which is indicative of chaos. Now here, in this case, we were driving the system into chaos. And here is the time series of the cardiac cell recording being made during that. And you see very irregular beating. But what we're going to do here is we're going to again plot previous interbeat interval against next interbeat interval. And when we do the Poincare plot, you see a very interesting, non-trivial, this is a little different from the ones we've seen previously, but it's another indicator of chaos. And the Poincare plot looks like this. Excuse me. Like that. And This is clearly a low-dimensional figure. Incidentally, if you made a mathematical function that looked like that and put it into your computer and iterated that as a discrete time dynamical system, that would indeed produce a chaotic response. So we're pretty confident that the chaotic response of the cell is an instance of deterministic chaos.